Good afternoon. Our Capstone project is restoration of heavily compressed audio files using deep learning. Our mentors are Dr. Dutt Joshi and Dr. Karamjit Singh Sandha. And now our team will introduce ourselves.
Hi, I'm Karamjit Singh Bedi and I'm from ECE.
Hi, I'm Abhinav Mehra and my branch is ENC.
Hello, I'm Aryaman Mittal and I'm from ENC branch.
My name is Angad Bagga and my branch is ENC.
I'm Ambar Sood and my branch is easy. So starting with the introduction, today I present a solution to one of the challenges we face in audio signal processing. The challenge is that in MP3 codec under high compression rates, there are impairments introduced. And this has yet to be tackled with deep learning techniques. So our project lies in a tailored architecture of GANs, which is Generative Adversarial Network. And we design it to reconstruct these heavily compressed signals and evaluate them for different compression rates. Our GAN-based neural network is trained on a diverse corpus of highly compressed music and speech files, which aims to rejuvenate severely degraded audio and therefore recapturing the lost information. In our project, we are using spectrogram as a representative domain for audio signals. This offers us a unique approach for signal restoration. So join us in exploring this DL solution.
So as Amber discussed, what is a generative adversarial network? So generative adversarial network or GAN are a deep class of deep learning models with two components, a generator and a discriminator. GANs are used to generate new data that resembles a given training set. The generator tries to create realistic samples, whereas the discriminator aims to distinguish between real and generated samples. What is a MP3 audio codec? MP3, officially known as MPEG Audio Layer 3, is a digital audio coding format developed by a German society. It gained popularity due to its ability to compress audio using lossy data compression techniques, reducing file size, while maintaining acceptable audio quality. What is a spectrogram? A spectrogram is a visual representation of the frequency spectrum of a signal over time. It shows how frequency distribution in a signal changes as the signal processes. They can be used to analyze the spectral content of a piece, identify different instruments or notes, and even study the dynamics of sound. What is a Mel spectrogram? A Mel spectrogram is a type of spectrogram in which the frequencies are converted to Mel scale, where the Mel scale is a perceptual scale of the pitches that listeners perceive as equal at a distance.
The methodology we've adopted is as follows. Our neural network consists of inputs in the form of spectrograms. These contain the spectral content of our audio snippets. A supervised learning approach is used to achieve efficient audio restoration. The loss function we've used is of two types, Wasserstein GAN and hinge loss. Initially, we had used Wasserstein loss. However, it produced meaningless gradients for our generator. So we shifted to hinge loss, which was used to minimize the distance during training. Our GAN architecture is used in a way that the model is trained on MP3 compressed audio files at 16, 32, and 40 kilobits. Next slide. In the simulation setup, the compressed audio files were split into 4 to 5 second audio snippets at a sampling rate of 44.1 kilohertz. The Mel spectrogram was calculated with a window size of 2048 and a hop size of 512 and 256. The model was trained for 1,000 iterations, which took approximately 25 hours. The results, initially, the discriminator outperformed the generator. So we had to fix it by making the generator improve 5 times per epoch. The hinge loss was set up with a gradient penalty of lambda is equal to 10 and the Adam optimizer with a learning rate of 10 raised to the power minus 4. Now, Karamjit will tell you about the model.
How exactly our model works is, this is where we load the dependencies. And these are the hyperparameters that we set. So for demonstration purposes, we set the epochs to 1, while the lambda, while the learning rate and the gradient penalty hyperparameters are set as the same. These are the metrics that we had used for an objective comparison of the original audio and the restored audio. So we've used signal to noise ratio and the mean squared error. And this is the definition of the hinge loss that we've used to train the GAN. This is the definition, description of the generator and the discriminator models. For a detailed description of these two models, you can refer to the report. Now we've loaded the songs. For demonstration purposes, we've selected a subset of our original corpus, but we'll be releasing the actual corpus once we open source this code. This is how we've trained the model. So we've trained the model on the subset, and initially the discriminator is trained. Now the discriminator decides to identify between the generated or the fake spectrograms and the real spectrograms. While the generator tries to fool the discriminator by creating restored spectrograms that closely resemble the original spectrogram. We save the model weights and then test it out. We tested it out on 6 snippets of 3 songs, and we decided to display the results on a website. Right. So this is a website that we've created for just to show an example. We'll try to show you an example by showing an original song, its compressed version, and the restored version.
First original.
I don't care if you buys you nice things, but I don't care if you buys you nice things, but I don't care if you buys you nice things, but
And finally, the restored one.
I don't care if you buys you nice things, but
Now we take a look at the SNR and the mean squared error of this very snippet, right? So when we tested this song, we only used the 32 kilobits version of this song as the input, and then restored it, which shows a very high decrease in the mean square error and an increase in the SNR.
So finally, to conclude the project, I would like to say that we have successfully implemented a GAN architecture designed to restore heavily compressed audio files with the firm belief that our project has immense potential to be widely adopted product, which is seamlessly integrated into every computer equipped with sufficient computational power. Finally, in terms of future work, our commitment to innovation and excellence compels us to extend our research into diffusion-based architectures specifically tailored for our model.